Okay, so this is a video for Friday, March 6th. Another day I'm not going to be here, so I'm making the video in advance. Hopefully you guys are watching this in class right now. Hopefully you printed off the notes already. If you haven't printed off the notes, maybe go do that. Okay, everybody's printed off the notes for the day. Okay, so yesterday we started off talking about redox. Let me just do a quick little bit of a review, just to remind you what redox was from yesterday. Redox. So redox really it refers to two reactions happening at once. There's the reduction reaction, and reduction, if you remember your that acronym Leo says GER, means that someone is going to gain electrons. If you gain electrons, you're being reduced. A really good example of a reduction equation then would be like, say, copper 2 plus might add 2 electrons and become copper solid. And one of the original definitions of reduction was an ore, or like a compound, getting reduced down to a pure metal. So that's reduction. That being said, someone cannot just randomly gain electrons, because you're not just going to find electrons just lying around on the street. You're going to have someone lose them. So maybe something like silver solid could then turn into silver plus, and maybe could lose an electron. And that would be the other half of redox. That would be the oxidization. And that, according to Leo says GER, is a loss of electrons. I really like the analogy of endo and exothermic. This reaction right here is kind of like an endothermic reaction. You need to absorb electrons, but you're going to need a simultaneous exothermic reaction where someone is emitting off electrons, like releasing them. The last thing we worked on yesterday then was we can actually combine these reactions using more or less a modified Hess's law. This reaction is not ready to be combined yet until I double everything. Because if I double everything, now these 2 electrons right here can cancel with these 2 electrons. And then we can put the whole reaction together. And I'm kind of running out of room here. That whole reaction would be Ag solid plus copper aqueous would turn into copper solid and silver aqueous. So this is what we focused on yesterday. A lot of terminology. If copper is being reduced, it's the oxidizing agent. And I have written right here, electrons are gained by the oxidizing agent. So this copper right here is going to be gaining those electrons because it itself is being reduced. And then electrons are lost by the reducing agent because this guy right here is actually being oxidized. So yesterday was a lot of terminology. Today then I want to talk mostly about this bullet right here. The electrons are really in like a hypothetical tug of war with each other, where there's a fight for the electrons. Last year when I taught you guys the bonding unit, we talked about the term electronegativity. And hopefully you remember a little bit about electronegativity. It basically was a ranking system that we used to help describe who was most likely to take electrons in a fight for electrons. Fluorine was the most electronegative. It has a number of 4.0. It's like the most electronegative thing out there. It really wants electrons. So hopefully you remember that concept. I want to apply that today. Each of these species right here really are fighting for electrons, and someone is going to win that fight. The person who's going to win that fight is the oxidizing agent. Copper wants electrons more than silver, and so copper is going to steal them away. Copper currently is a cation, is positive, and when it comes in contact with the silver, that copper is going to say, I want your electrons. Kind of like, I don't know, the typical analogy of a bully trying to beat someone up for their lunch money. Copper is going to say to silver, hey buddy, you have electrons, and give them to me. And so then copper takes those electrons and becomes solid copper, and poor old silver has to become positively charged because it lost its electron. So hopefully that makes sense. The idea of a tug of war, or like a competition, or maybe like a fight. Someone is going to win. The winner is going to take the electrons. Okay. And that's where this next term comes in here, is if the winner is someone different, I guess, a reaction can occur. So like since copper, let me go back up here, since copper is going to win this fight and steal silver's electrons, new stuff will be made and you'll have new products. Hypothetically though, let's say silver wins the fight. Well then silver will just keep their electrons and nothing would happen. It's almost like a heavyweight fight with like a title belt. If copper wins, copper takes the belt and copper becomes the new champion. Or what if silver wins the fight? Well, if silver was actually stronger than copper was right here, then no reaction would take place because silver would just hold on to its electrons and swat copper out of the way and say, no, you can't have my electrons. And that describes the term spontaneous. So if someone wins, a reaction spontaneously happens, like it happens at a fairly decent rate. Whereas it's possible that no reaction could occur. It just depends on who wins the fight. That's my goal today, is to show you in the video how that's going to work. So I'm going to skip way ahead here to a table that I referenced the other day in your book. This is a table of a whole bunch of reduction half reactions. And I actually pointed out yesterday that we use this double-sided arrow because in this direction things are being reduced. But if you considered the arrow to be going backwards, they'd be being oxidized. So anyways, here's how this table works. It's a ranking of who wants electrons the most. The person who is up here is the strongest oxidizing agent. And hopefully you have that written in your book from like whoever was using your data book on the diploma. Because I always tell my kids the first thing you should do is write that this guy right here is the strongest oxidizing agent. So what is an oxidizing agent? Well, an oxidizing agent is someone who gets reduced. And someone who gets reduced is someone who gains electrons. Well, this means that the strongest person who like wants electrons is fluorine. And hopefully that makes sense because fluorine, according to your data table, is the most electronegative. It really, really wants electrons. And so if fluorine was in a fight, fluorine is the king of the ring. Whereas like say chlorine, chlorine's not bad, but it's not quite as good as fluorine. If chlorine and fluorine were in a fight, fluorine would win. If bromine was in that fight, fluorine would win, and then chlorine would be second and bromine would be next. So there's kind of a ranking system telling you who is most likely to gain electrons. Conversely, on the bottom side of your table, way over here, I don't have the whole table drawn, but the strongest reducing agents are down here, and these are the guys that are the most likely to lose their electrons. Maybe I have the full table on another slide somewhere here. There I do. Lithium. Lithium is actually the strongest reducing agent, which as a reducing agent means you're getting oxidized. You should really think of lithium actually going backwards the other way here. Lithium would really, really, really love to lose an electron, whereas fluorine would really love to gain electrons. And so if fluorine and lithium came in contact with each other, a reaction would totally occur because this person really wants to gain electrons, this guy really wants to lose electrons. Okay. If they're at extreme ends of the table, that works really well. Sometimes though things are like more towards the middle. For example, let's say silver and, what was the other one we did? Silver and copper, was it? Here's silver plus. Where are you, copper? There's copper. This is the reaction we just did. Silver plus and copper solid, I think is what I just did as a reaction. Here silver is fairly likely to want to gain electrons. It's pretty good on the side of the table. Copper is maybe a little further up the table. Here's how this rule works. If this guy is like a downhill, like a downward arrow, then a reaction is likely to happen. We call that a spontaneous reaction, where silver is going to take the electron and become silver solid, and copper is going to lose the electrons and become copper 2+. Let's say, though, that it was tin trying to react with copper. This orientation, you would say, is not spontaneous, and this orientation you'd say is spontaneous. This reaction will occur, and this reaction will not occur. And it basically just has to do with the ranking system. This guy right here is stronger than this guy, so he wins the fight. Whereas this guy right here is weaker than this guy, so he loses the fight. So here, tin and copper would do nothing, because tin is not strong enough to steal copper's electrons. Whereas here, silver and copper, silver is strong enough to steal copper's electrons. So I've got a bunch of diagrams in here. Probably here's the best one. If your OA is above your RA, the reaction will occur. This diagram here didn't really work all that well. Let me just scratch this and redraw another one. If this OA is below this RA, then it's non-spontaneous. I have no idea why this reaction didn't. That diagram totally got screwed up. So, let me walk through some of the stuff I skipped here, just to make sure I'm doing a thorough job. Let's start here. Oxidizing agents and reducing agents are embarking in a fight. If the oxidizing agent is strong enough, he will steal the reducing agent's electron, just like that analogy I gave of stealing lunch money. So if these guys, if the orientation is correct on that data booklet, if this guy is strong enough, he'll steal his electron. So electrons always go from a reducing agent who is oxidized, who loses his electron, to the oxidizing agent who is reduced, who then gains the electron. So hopefully that makes sense. I guess I just have more examples here, but I think you guys can probably just read through those. Here's an important note. Oxidizing and reducing is an actual process. Like, reducing means that you are gaining electrons. Oxidizing means that you are losing electrons. Whereas the oxidizing agents and reducing agents, those are the actual chemicals. Just want to make sure these words are being used right. Okay, let's maybe just do some examples here. Really, the key is the data table. If the arrows from the substances that you're starting with, so like the starting things are your oxidizing agent and your reducing agent, if it's that orientation, this guy is strong enough to steal this guy's lunch money being electrons. Whereas if it was like, say, this guy and this guy, tin is not strong enough to steal copper's electrons. So this is like a little grade 10 student trying to pick on a grade 12 student. It's not going to work. This is a grade 12 student picking on a grade 4 student. So that will work. Hopefully that analogy makes sense. So, this more or less just shows you what I always tell my kids to write down in the data booklet. Strongest oxidizing agent is at the top over here. Strongest reducing agent is at the bottom over here. And it's a ranking system. This guy is the king of the ring for stealing electrons. This guy is the king of the ring for giving away electrons. Or maybe he's like the biggest wimp, I guess, because he loves to give away his electrons. Okay, let's do some examples. Let's find one here. So my question here is, figure out whether or not these compounds will react. By that I mean, if they will react, they have an orientation like this, and we say it's spontaneous. That's the word we use. Spontaneous. If they don't react, it'll be that orientation. So the way I recommend you do this then is find all of the species on your data table. Some of you may have tables that are really marked up, because I always tell my kids to like circle stuff. What I may do one day is I might try to make you guys a transparency slide. Some kids discovered they like using transparencies because they could write all over this and then erase it and start again. So let me try an example here. Here I have bromine liquid. It takes a while to get used to your table and know where things are, but here is where bromine liquid is. So I'll just try to pause so that you guys can try to find these things. Then I would suggest, let's try to find these species right here. This is going to be the iron 2+ version, because of that 2 right there. And then there's also a nitrate. So if I try to find the iron 2+ version, I'll discover one right there. It looks like the nitrate's going to be a spectator ion. Some people might notice that nitrate is sitting right here, but it also requires H+, and we don't have H+. As a general rule here, if the equation doesn't have everything listed, you can't use it. So since we don't have this H+, we can't use this equation. So, and then here's my question. Will bromine liquid have enough strength to steal electrons from iron 2+? And I'd say yes. Based on this orientation, bromine is higher on the ranking chart than iron, so bromine will win this fight. So bromine is going to steal some of iron's electrons. So what's going to happen is this bromine will turn into bromine negative. So that means one of the products will be bromine negative. Two bromine negatives, I guess. And then this reaction is going to go back the other way. This iron 2+ will become that iron 3+. Wrong way. Usually we would like ignore the nitrate because it's a spectator ion. We might have to balance as well. Probably we're going to need to do some 2s. Anyways, I'm not actually going to worry about balancing because I want to focus on balancing another day. We actually have a whole lesson for balancing. But my question here is, will it react or not? And I would say based on the downward arrow, yes, this will react. So let me try another one. Let me just erase this. So feel free to make a mess out of this chart here. Like I said, some of you may have data books where like clearly the person using it made a lot of mess. Like they circled and highlighted stuff everywhere. So I want to look for copper 2+. I want to look for nitrate, and I want to look for gold solid. Here is copper 2+. Pardon me. Nitrate is right here, but again, I don't have hydrogen, so I can't use that. Gold solid is way up here. Is copper 2+ then strong enough to steal electrons from gold solid? I would say no, it's not. Gold solid really wants to keep its electrons, actually. This gold plus right here would actually really like to take electrons, so this guy's not going to give away his electrons. So in this orientation, I would say that no reaction can happen. Two last examples. This one involves iron 3+, Cl-, and copper solid. Just erase these. Feel free to pause this as you're searching for items. One thing I've discovered is that it takes you a long time at first to find where things are on your data table. So like if you need to, pause the video. Just to save time for me, I'm going to keep going. But make sure you pause if you need to. I need an iron 3+, which I know where that one is. I need a chlorine negative, which there's one right there. Based on those two guys, no reaction is going to happen. There is copper solid, though, which is right here. Can a reaction take place? I'd say yes. Iron 3+ can totally react with copper. The chlorine and the iron won't react with each other, but iron is strong enough to take an electron from this copper. This copper will give away 2 electrons, and this iron will add electrons. We'll balance another day. I have a whole day just based on balancing. So my whole goal today is just to figure out whether a reaction occurs. So yes, this reaction would occur. I believe you'd make chlorine 2+, and the iron became a 2+, I think. Okay, last one. This one here I wanted to illustrate that iron could be a 2 or a 3. Iron 2 is on the table in a few other places. So let me just erase here. Here was the iron, well, let me actually recircle everything. Here was the iron 3+. There's the 2+. There's the copper. Everybody so far is in this column. You always have to have one oxidizing agent and one reducing agent. So you can't have a reaction if everybody's in the right-hand column. But there is actually an iron 2+ on both sides of the table. There are actually some things that are on both sides. So what ends up happening then is that in terms of like these guys right here, iron 2+ is not capable of reacting with either the copper or this iron right here, or even this chlorine right here. So this iron right here is kind of a wimp at taking electrons. Can it win a fight? Sure. This iron right here could win against zinc. So like in terms of an analogy maybe, this iron is like a 4th grader. This 4th grader cannot win a fight against a 7th grader, or an 8th grader, or a 9th grader. But this 4th grader could have beat a 1st grader or a 2nd grader down here. But according to what we have here, this reaction, I would say there is no reaction. Hopefully that makes sense. We're going to do a whole lab on this on Monday to help like demonstrate reactions. So make sure you print off that lab for Monday. I'd like to... you guys can read over the rest of this stuff. It's really the same thing. If it's in this orientation here, it doesn't happen. Or it does happen. If it's in this orientation here, it does not happen. Okay, last thing. I want to show you some examples of some diploma type questions. This is one that was a diploma question at one point. I just wrote it out. Hopefully you have this one in your notes. Here's how you might solve something like this. Here you have a cobalt 2+ and an indium solid, and it claims that this is a spontaneous reaction. So what we're going to do is we're going to try to make our own data table, and it might look like this. Cobalt 2+ reacts with indium salt. So I have to put the cobalt 2+ above the indium in making like my own table. What that means then is that this cobalt actually is going to form cobalt solid, and this indium going backwards would form indium 3+. And so that gets my table started with this guy and this guy in a downward trajectory. And then I find the next reaction, and it says it's also spontaneous. It says that a copper will be spontaneous with a cobalt. Well, if copper 2+ needs to be spontaneous with cobalt, that means copper 2+, the only place it can really go is up here so that it can be spontaneous with the cobalt. Because I couldn't put copper down here, because that wouldn't work. I couldn't put copper down here, because that wouldn't work. So if copper and cobalt do react with each other, because copper is able to steal cobalt's electrons, then the copper will turn into copper solid, and this guy turned backwards to that guy. And so now my table is getting formed just a little bit more. And I do the last example. Copper 2+ and PD solid do not react. Well, if here's where copper 2+ is, so it's already like on my table, where does PD solid go? Well, it's a solid, so it has to go on this side here. If I put PD solid right here, that would have reacted. If PD solids go down here, it would have reacted. So the only place PD solid could go would be up here, so that it doesn't react. It doesn't actually tell me what would form PD solid, so I'm just going to guess that it's PD like 2+. And now I've made myself my own table. They love to give a question like this on every diploma. Like this is one of their standard go-to questions year after year. And the idea is they always pick elements that aren't on your data table so that you can't just look it up and know how the table goes. And then they usually ask a question where like the way they phrase the question is, who is the strongest reducing agent? And you might say, well, this guy is the strongest reducing agent. Or they might ask, well, who's the strongest oxidizing agent? And you'd say, well, this guy is the strongest oxidizing agent. They love to make it numeric response. And so sometimes they would then say, like, they'd give you like a legend. They'd say that like PD solid is a 3, and Cu solid is 2, and CO solid is 1, and IN solid is 4. And they might say rank the reducing agents from strong to weak. So then you'd say, well, your strongest reducing agent was this guy. So that means the first blank would be 4. And then the next strongest reducing agent would be cobalt. So that would be your 1. And then your next strongest reducing agent would be your copper solid, which would be 2. And then your least strong reducing agent would be the PD, which I made 3. I just kind of randomly chose numbers for these, by the way. So I'll show you lots of examples of diploma questions like this. Actually, that's what my last slide is. I think this is the last one there. So maybe pause the video, see whether you can figure out how to solve this question on your own. And then once you've given it a try, like I said, this is an old diploma question, watch the video, see whether my process makes sense. So pause the video, try it, or I mean, if you have no clue what you're doing, just watch the video, I guess. So here's how I'd start. U3 plus and LA are not on my data table. That's kind of the whole point. They're going to pick things that you can't look up. So I know that U3 plus is going to need to go downhill to LA solid. It means that my U3 plus made U solid, and that my LA solid must have gone backwards to make LA3 plus. And so now I've got my table started. Then I look at the next reaction. It says that Y3 plus and U solid do not react with each other. So I'm going to find some places that Y3 plus could go. I'm going to put it in 3 locations. Y3 plus could be either here, or here, or here. And I've got to figure out which locations this is logical in. And there's one location that doesn't fit for sure. If it says there's no reaction, I can't have this guy being above that guy. I can't have this guy being stronger than that one. So this top one is out. Unfortunately, I don't actually know which of these 2 places the Y3 plus is going to be, because both of them go uphill to U solid. So I'm just going to kind of leave them there, and I'm going to figure out which one is the correct one in my last step. So then last step. Y3 plus and LA solid do react with each other. So which one of these 2 red ones is the right one? Well, I'd say this top one is. This Y3 plus is above the LA solid. So then this one works. Whereas this one up here would be uphill, non-spontaneous. So then it's not this guy or this guy. So then I'm just going to double check my work. U3 plus and LA solid are spontaneous. This reaction will occur. This guy is strong enough to steal that guy's electrons. Y3 plus and U do not react, which means this guy went uphill, and that was true. I've written it in an uphill orientation, meaning this guy is not strong enough to steal that guy's electrons. And then last one, is Y3 plus above LA solid? And this guy is above LA solid, meaning this guy is strong enough to steal that guy's electrons. So now to answer the question, who are the oxidizing agents? Oxidizing agents are people who themselves are reduced, and reduced is gain of electrons is reduced. So the person who was gaining electrons was these guys over here. They're all gaining electrons. So the strongest oxidizing agent was U3 plus, then Y3 plus, then La3 plus. If this was like a ranking system, maybe like how teams get ranked going into provincials, this is the number 1 seed, this is the number 2 seed, this is the number 3 seed. So this guy should win against that one, this guy should win against this one, but this guy will not win against that guy. So right answer was B. So I hope that makes sense. It's a very simple concept once you've done a lot of examples. Like, it's something you're going to want to practice. But I can really break it down into like this slide right here. If it goes in this orientation, this OA is strong enough to win a fight for electrons against this RA down here in our ranking system. This is like the 2 seed beating the 6 seed. Whereas here, the 6 seed is not able to beat the 2 seed in this orientation. So here, 2 will beat 6. Here, 6 cannot beat 2. So no reaction happens here. Here, a reaction does happen. Later we'll talk more about like how to balance them and what to do with them. But if you can understand how to use this table, wherever my table is, if you understand how this table works, and hopefully it makes more sense why other students have had markings all over it now, what I'll try to do is I'll try to make some overhead copies for you to use of this table so that you can then mark it up with like an overhead pen and then erase it all, and then you can use this table over and over again. Try not to write in this on pen. You probably have markings all over your table already though, because often kids are just circling stuff going, I've got stuff there and there and there, and oh look, there's a reaction and there's a reaction and there's not a reaction. Okay, I'm going to call it quits. Monday we're going to do a lab, and hopefully I can help you visualize this. If you have any questions, you can feel free to ask the sub for the day. I believe he's a chem teacher, so he should be able to help you. Otherwise, ask me on Monday. In terms of stuff to do, I do have some textbook pages to look at, and if you have a Snap workbook or you want to steal one off the front table, you could. Otherwise, make sure you've finished all of your labs, all of your projects, all of your assignments, and we'll see you guys Monday.